Welcome back to structural dynamics class. So, in this module we will study resonant frequency and half power bandwidth. So, first of all let us discuss what is resonant frequency. So, resonant frequency is like when resonance takes place. So, if we apply a static load on any system or any member, it deflects. But slowly if we increase the frequency of the load, application of the load, then the deformation increases. So, if the frequency of the load application, that is frequency of the load, or you call it as forcing frequency, if it is matching with the natural frequency of the system, large amplitude of displacement, velocity, accelerations take place. But like what are the special conditions in this one? When is the acceleration maximum? When is velocity maximum? When is displacement maximum? That we are going to study in this class. And also like how these maximum accelerations can be controlled, displacements and velocities can be controlled, that we are going to discuss in the class. In addition to it, like if we have a RD curve means dynamic amplification factor, that curve where RD is a function of R, that is frequency ratio. What are the properties in that curve? That is also we are going to study. Now, if you look at RD curve, it looks like this. So RD formula, that is 1 by under root 1 minus R square whole square plus 2 zeta R. This is RD. This represents RD, which is a function of R and zeta. Now, it is defined as the forcing frequency at which the largest response amplitude occurs, resonant frequency. So, largest response amplitude. So, here we have three responses: displacement as response, velocity as response, and acceleration as response. Now, let us look at displacement response when it is becoming maximum. So, when it is going to resonating frequency. So, for that we need to differentiate this with R, because it is a function of R. We need to differentiate it with R. So, delta RD divided by delta R is equal to 0. So, if we maximize and minimize, and first derivative should be 0 to get the maximum value. So, we are differentiating that, and if we differentiate it and equate it to 0, so what we get out of it is omega is equal to under root 1 minus zeta square. In a way, R is equal to under root 1 minus zeta square. So, this is what we will get from the derivative of that, and if we equate it to 0, we get R is equal to under root 1 minus zeta square. So, that means omega is equal to omega n under root 1 minus zeta square. So, that is a resonating frequency for displacement. Now, let us look at for velocity. So, what is the resonating frequency for velocity? So, if we differentiate it with R, so delta RV by delta R and equate it to 0. So, if we equate it to 0, omega becomes equal to omega n. So, that means R is equal to 1 value we will get, R is equal to 1. So, usually we believe that resonating condition occurs when omega is equal to omega n. So, that resonating condition occurs for velocity, not for displacement or for acceleration. So, usually when we talk resonating condition, when frequency matches, that is omega is equal to omega n for velocity, that is. And in some special case means when no damping is there, all three becomes equal. So, as you can see, the third one, delta RA by delta R, if it is equal to 0, so that means what we have first derivative of RA function, if we are making it equal to 0, what relation we will get? So, that is omega is equal to 1 by under root omega by omega R is equal to 1 by under root 1 minus zeta square. As you can see, omega is equal to omega n under root 1 minus zeta square. So, in displacement resonating condition, zeta is there. In acceleration resonating condition also zeta is there, and velocity resonating condition zeta is like insensitive. So, that means omega is equal to omega, that means R is equal to 1. Now, if we substitute these values in the original equation, so what we will get, we will look at it. But before that, let us look at if when zeta is equal to 1, that means when 0, that means when 0 damping case, omega is equal to omega n condition we will get, velocity anyway omega is equal to omega n, and here if it is 0 again omega is equal to omega n. So that means under no damping condition all three are same. Now what is the value of this dynamic amplification factor at resonating frequency? As you can see, Rd is equal to 1 by 2 zeta under root 1 minus zeta square. That means Rd can be controlled with damping at resonating condition, and here at velocity can be controlled at resonating condition by damping, and acceleration can be controlled by 1 by 2 zeta under root 1 minus zeta square. So that means what, at resonating conditions damping controls the amplitude of vibration. So in real systems damping will be present. Damping is 0 condition is the ideal condition. Now let us look at the Rd curve and what properties it has. So let us look at this statement, that is when omega A and omega B are the forcing frequencies on either side of the resonating frequency, at which amplitude u0 is equal to 1 by root 2 times of resonating amplitude. Then for all small values of zeta there is a relationship. Let us discuss that. So this is a Rd curve. So dynamic amplification factor for Rd. If you look at this one, the curve, okay, the definition says that omega A and omega B frequencies on either side. So this is omega A and this is omega B, frequencies are on either side of resonating frequency. Resonating frequency is this one. So somewhere here, okay, somewhere in the middle, at which amplitude u0. So this is u0 and that is 1 by root 2 times of this resonating amplitude. Okay, resonating amplitude is 1 by root 2 times of resonating amplitude. Then the relationship will be omega B minus omega A divided by omega n is equal to 2 times of zeta. So that means what, it is this area, you can look at it. Okay, so this is like omega A B minus omega A divided by omega n into 2 times of zeta. So how this equation we are getting, let us look at it. So displacement response factor Rd, we already know that 1 by under root 1 minus r square whole square plus 2 zeta r whole square. Now at resonating condition for displacement is Rd is equal to 1 by 2 zeta under root 1 minus zeta square. So now according to the definition, this Rd should be equal to 1 by root 2 times of resonating amplitude. So this is resonating amplitude, 1 by under root 2 times is equal to Rd. So that's what is given. Rd is this function. So if we look at take this point, so this point is equal to 1 by root 2 times resonating amplitude. So we know resonating amplitude, this is resonating amplitude. So 1 by root 2 times of resonating amplitude is equal to this function. So the function value we know. So if we equate this one and work it out and simplify, so what happens is finally we will get r square as 1 minus 2 zeta square plus or minus 2 zeta under root 1 minus zeta square. So if we take the roots of this one, we will get that r is equal to plus or minus under root 1 plus or minus 2 zeta square. So by expanding in Taylor series this one, because it's a bracket to the power of minus 1 by 2, that is square root. So if we expand it, it becomes r approximately equal to 1 plus or minus zeta. R means omega by omega n is approximately equal to 1 plus or minus zeta. So if we expand it further, if we further simplify it, then two roots are there. Omega b minus omega a divided by omega n is equal to 2 times of zeta. So this is what is the definition of that. As you can see that if omega a and omega b are the forcing frequencies on either side of resonating frequency, at which the amplitude is u0 is equal to 1 by root 2 times of resonating amplitude. So at two sides, this one and this one. So these frequencies are omega and omega b. So they are related to this curve or related to damping in this form. So if we know this Rd curve, we can find out the damping in the system. So how we can do is, we know the resonating amplitude, and then just mark the value of 1 by root 2 of that, peak value you take, and 1 by root 2 of that you mark the value here. So, two things. So, let me explain once again here. So, we have this resonant response curve. So, this is peak. Okay. So, take that peak value and divide by 1 by root 2. So, then 1 by root 2 you mark a line, this value is there, this value is there. So, 1 will be omega A and omega B is this one, omega A is this one. So, omega B minus omega A divided by omega n is known value, that is equal to 2 times zeta. So, with this curve also we can find out what is the damping present in the system. So, in this class we have studied about two things. One is what is the resonating condition for displacement, resonating condition for velocity, resonating condition for acceleration. So, this we feel omega forcing frequency when it is equal to natural frequency, resonating condition occurs, that is true, but it is only for velocity under any given damping. But for displacement and for acceleration it is slightly away from the natural frequency because of the presence of damping. Damping is not present, then all three resonating conditions are same. Omega is equal to omega n, resonating condition occurs for velocity, displacement as well as acceleration. Then we have derived what is the maximum value of Rd, Ra and Rv at the resonating condition, that we have worked out. And next is a half power bandwidth we have worked out. So, the relationship between damping and the frequency. So, if given Rd curve, how can we find out the damping present in the system? So, it is very simple. First we have to locate the peak value, peak amplitude in that Rd value, and then divide that by root 2. Then we get 2 points on the Rd curve. So, corresponding frequency if we measure, that will be omega B and omega A. So, omega B minus omega A by omega n is equal to 2 times of damping. So, like using this equation we can measure the damping present in the system.